In the last segment in this module, I want to show you a general attack that affects many implementations of Mac algorithms, and there's a nice lesson to be learned from an attack like this. So let's look at a particular implementation of HMAC verification. This happens to be an implementation from the Kezar library that happens to be written in Python. So here's the code that's used to verify a tag generated by HMAC. This code is actually simplified. I just wanted to kind of simplify it as much as I can to get the point across. So basically what the inputs are the key, the message, and the tag bytes. The way we verify it is we recompute the HMAC on the message, and then we compare, say, the resulting 16 bytes to the actual given signature bytes. So this looks perfectly fine. In fact, anyone might implement it like this, and in fact, many people have implemented it like this. The problem is that if you look at how the comparison is done, the comparison, as you might expect, is done byte by byte. There's a loop inside of the Python interpreter that loops over all 16 bytes. And it so happens that the first time it finds an inequality, the loop terminates and says the strings are not equal. And the fact that the comparator exits when the first inequality is found introduces a significant timing attack on this library. So let me show you how one might attack it. So imagine you're the attacker and you have a message M for which you want to obtain a valid tag. Now your goal is to attack a server that has an HMAC secret key stored in it. And the server exposes an interface that basically takes message MAC pairs, checks that the MAC is valid. If the MAC is valid, it does something with the message. And if the MAC is not valid, it says reject. Okay, it sends back to the originator the message reject. So now this attacker has an opportunity to basically submit lots of message tag pairs and see if it can deduce the tag for the particular message for which it wants a tag. And here's how we might use the broken implementation from the previous slide to do just that. So what the attacker is going to do is submit many message tag queries where the message is always the same, but with the tag he's going to experiment with lots and lots and lots of different tags. So in the first query, what he's going to do is just submit a random tag along with the target message. And he's going to measure how long the server took to respond. The next query that he's going to submit is he's going to try all possible first bytes for the tag. So let me explain what I mean by that. So the remaining bytes of the tag that he submits are just arbitrary. It doesn't really matter what they are. But for the first byte, what he'll do is he'll submit a tag starting with a byte 0. And then he's going to see whether the server took a little bit longer to verify the tag than before. If the server took exactly the same amount of time to verify the tag as in step 1, then he's going to try again, this time with byte set to 1. If still the server responded very quickly, he's going to try with a byte set to 2. If the server responded quickly, he's going to try with a byte set to 3, and so on, until finally, let's say when the byte is set to 3, the server takes a little bit longer to respond. What that means is actually when it did the comparison between the correct MAC and the MAC submitted by the attacker, the two matched on this byte, and the rejection happened on the second byte. Aha, so now the attacker knows that the first byte of the tag is set to 3, and now he can mount exactly the same attack on the second byte. So here, it's going to submit a tag where the second byte, here, let me use a different color. So it's going to submit a tag when the second byte is set to 0, and it's going to measure whether this took a little bit longer than in step 2. If not, he's going to change this to be set to 1, and he's going to measure if the server's response time is a little longer than before. Eventually, let's say when he sets this to, I don't know, when the byte is set to 53, say, all of a sudden the server takes a little bit longer to respond, which means that now the comparator matched on the first 2 bytes, and now the attacker learned that the first 2 bytes of the MAC are 3 and 53, and now he can move on and do the exact same thing on the third byte, and then on the fourth byte, and so on and so forth, until finally the server says, yes, I accept, you actually gave me the right MAC, and then it will go ahead and act on this bogus message that the attacker supplied. So this is a beautiful example of how a timing attack can reveal the value of a MAC, the correct value of the MAC, kind of byte by byte, until eventually the attacker obtains all the correct bytes of the tag, and then he's able to fool the server into accepting this message tag pair. The reason I like this example is this is a perfectly reasonable way of implementing a MAC verification routine, and yet if you write it this way, it'll be completely broken. So what do? So let me show you 2 defenses. The first defense, I'll write it again in Python, is as follows. And in fact, the Kezar library exactly implemented this defense. This code is actually taken out of the updated version of the library. The first thing we do is we test if the signature bytes submitted by the attacker are of the correct length. Say for HMAC, this would be, say, 96 bits or 128 bits, and if not, we reject that as an invalid MAC. But now if the signature bytes really do have the correct length, what we do is we implement our own comparator that always takes the same amount of time to compare the two strings. So in particular, this uses the zip function in Python, which will essentially, if you are giving it two 16-byte strings, it will create 16 pairs of bytes. So it will just create a list of 16 elements where each element is a pair of bytes, one taken from the left and one taken from the right. And then you loop through this list of pairs. You compute the XOR of the first pair and you OR that into the result. Then you compute the XOR of the second pair and you OR that into the result. And you notice that if at any point in this loop 2 bytes happen to be not equal, then the XOR will evaluate to something that's non-zero, and therefore when we OR it into the result will also become non-zero, and then we'll return false at the end of the comparison. So the point here is that now the comparator always takes the same amount of time. Even if it finds a difference in byte number 3, it will continue running down both strings until the very end, and only then will it return the result. So now the timing attack supposedly is impossible. However, this can be quite problematic because compilers try to be too helpful here. So an optimizing compiler might look at this code and say, hey, wait a minute, I can actually improve this code by making the for loop end as soon as an incompatible set of bytes is discovered. And so now optimizing compiler could be your kind of Achilles heel when it comes to making programs always take the same amount of time. And so a different defense, which is not as widely implemented, is to try and hide from the adversary what strings are actually being compared. So let me show you what I mean by that. So again, here we have our verification algorithm. So it takes as inputs a key, a message, and a candidate MAC from the adversary. And then the way we do the comparison is we first of all compute the correct MAC on the message. But then instead of directly comparing the MAC and the signature bytes from the adversary, what we're going to do is we're going to hash one more time. So we compute a hash here of the MAC, we compute a hash of the signature bytes. Of course, if these two happen to be the same, then the resulting HMACs will also be the same, so the comparison will actually succeed. But the point is now, if sig bytes happen to equal MAC on the first byte but not on the remaining bytes, then when we do this additional hash layer, it's likely that the two resulting values are completely different, and as a result, the byte-by-byte comparator will just output on the first iteration. The point here is that the adversary doesn't actually know what strings are being compared, and as a result, he can't mount the timing attack that we discussed earlier. Okay, so this is another defense. At least now you're not at the mercy of an optimizing compiler. The main lesson from all of this is that you realize that people who even are experts at implementing crypto libraries get this stuff wrong. And they write code that works perfectly fine, and yet is completely vulnerable to a timing attack that completely undo all security of the system. So the lesson here is, of course, you should not be inventing your own crypto, but you shouldn't even be implementing your own crypto because most likely it'll be vulnerable to these side channel attacks. Just use the standard libraries like OpenSSL. Kezar is actually a fine library to use that would reduce the chances that you're vulnerable to these types of attacks.